Hey everybody, it's Mr. Carr again. Today we're going to be looking at 4-7 day one. Today, we're going to tie back to our trigonomic functions when we deal with specifically with triangles instead of graphing and everything like that. But now we're not going to be using right triangles anymore. That's what you did in the past. You used to solve right triangles to find all the missing sides and angles. Now we're going to look for oblique triangles, meaning we have, excuse me, oblique triangles so that we don't have a right angle is basically what we're getting at. Today we're looking at law of sines and law of cosines, and the next one we'll talk about is areas of those triangles. So for now, let's talk about what is a law of sines. If triangle ABC has side lengths A, B, and C representing the lengths of the sides opposite the angles with their measures, okay, angle A, angle B, angle C, then we can say the ratio of sine of A divided by A equals the sine of B divided by B equals the sine of C divided by C. Couple things to mention with this. The way this is drawn on here, notice that it's across these angle measures is their lowercase versions. That's typically how you're going to see that in this unit. We'll use the lowercase letters across from the capital letters for the angles. So capital letters, angles, lowercase for sides. So these ratios, like they always match up to each other. You put them in that sine of A over A, sine of B over B, sine of C over C. Now, because these are all ratios and proportions, we could also write it like this. We could flip everything if we wanted to. Okay. This might help in your solving process. It depends on what you have and what you're looking for. So it's bottom line is you take that side across and set them up on there. Now, here's an example of how we can use that. Here's the key thing. Before you can do law of sines, you have to have an angle side pair from across from each other. I cannot set this problem up if I don't have that, which you'll see in the when we talk about law of cosines. Okay, so solve triangle LMN, round side lengths to the nearest tenth, and angle measures to the nearest degree. I'm going to start with finding angle N here. So when it says solve it, we want to find all, remember from before, solving a triangle means find all the missing sides and angles. I'm going to start with angle N because that's going to be the easiest thing to do. I'm simply going to take 180 minus 112 minus 29 here. Okay, that's going to tell me that third angle. I don't have to do any rounding at that point. I just know what it is. So the measure of angle N here, second. Okay, so when I do that right there, so 180 minus 112 minus 29 gives me 39 degrees. Okay, now to find my missing side legs for N and M, I'm going to set up my ratios. So since I have 22 and 29, I personally like to do this. If I'm looking for side lengths, I'm going to do this version where I do A over the sine of A. I want to put those on top. So my first ratio I'm going to do 22 divided by the sine of 29. Okay, so that's the one that's I know. Everything else needs to still be set up. So for example, N is going to go over the sine of 39. And I'm going to do it again. 22 over the sine of 29 equals M over the sine of 112. When you do these problems, because I'm doing everything in degrees, make sure that your calculator is in degrees, okay? So sine is going to be done in degrees in every single case here. From here, I can multiply both sides by sine of 39. So I get 22 times the sine of 39 divided by the sine of 29 is going to give me n. Same thing here. I'm going to multiply both sides by the sine of 112. Running out of space here. Whoops. Okay, so I'm going to have 22 times the sine of 112 divided by the sine of 29, and that will equal to m here. I like doing it this way so that once it's in this scenario, I've done all my algebra steps, I've done my cross multiplying, or I just multiply both sides there. Now I can just plug this in my calculator all at one time. Just make sure it's in that fraction format. Okay, so give me 1 second here. Okay, so once I plug this in my calculator, in this first case, I'm going to get 28 point, and it's going around to the nearest tenth. So it's going to be 28.6 for n. Yeah, I feel like I should do approximately equal to because that's technically what I'm doing here. And then the second case, when I do this and I plug this in my calculator, I get 42.1 for my value of m. Okay, and that's everything I needed. I was missing three pieces. I had angle n, side m, and side n. Angle n is 39, side n, and side m there. Okay. We can also use this in a word problem. Whenever you do any of these, when you're anytime you're trying to figure out what's going on in the scenario, draw it out. Okay. So the ballooning, the angle of elevation from the top of a building to a hot air balloon is 62 degrees. So I'll go ahead and I'll put the top of the building here. Okay. Hot air balloon is somewhere out here. Okay. The angle of elevation is 62 degrees. The angle of elevation to the hot air balloon from the top of a second building that is 650 feet due east is 49 degrees. So that's okay. Second building that is 650 degree, or sorry, that's a little confusing there. Okay, so 650 due east. Here's my second building. Okay, that angle of elevation there is 49 degrees. I'm going to assume from this, I'm going to say that the it's going to be sorry, I can't think about that one. From my reading of this, the buildings are probably going to be the same height. I think that we're assuming that in this case. I don't like assuming, but I'm pretty sure that's what this is going to get at here. Okay, so find the distance from the hot air balloon to each building. So what we're looking for is this distance here and this distance here. So I'm going to redraw this triangle out, make it a little bit easier for myself, but that's my scenario. I got two buildings, angle of elevation in both cases there. So here's my triangle that I'm working with. Okay, so this is 62 degrees. I'm going to hold off on labeling the 49, but this is going to be 650. And then this, we'll call this X and this is Y. So X is the distance to the first building, Y is the distance to the second building. So because of the 49 here, I can model, I know what this angle is going to be because it makes this straight line like this. Okay, so I can do this angle here is just 180 minus the 49 there. That's going to give me 131 degrees here. So I can start with taking 180 minus 49, tells me this is 131 degrees. From there, I don't know why I wrote 650 degrees earlier. My bad on that. Get rid of that part. So 650 feet. So in this case, I've got two angles now. I still need one more angle because I need this angle as an angle side pair in order to use my law of sines. So in this case, I can do 180 minus 131 minus 62. Okay, so I'll do that real quick. 180 minus 131 minus 62. And that's going to give me 1 second here. Sorry about that. I caught myself in my mistake here. My model is going to be a little bit different. And it has to do with like a little bit of real life here. If the first building was here and the second building was here and the hot air balloon was this side, it would have created, this is actually creating a smaller angle than this one. But when I label them, that's the bigger angle and smaller angle. So actually everything needs to flip in my diagram here. So that's what I'm going to do real quick here. Two buildings apart, still going to be 650 there. But now it's going to look more like this. Okay. This is going to give me 62 degrees here. This will be 49 degrees here. So sorry about that confusion there because I got a little bit mixed up with those parts there. Okay. Probably word problem should have been a little bit more clear, I guess, where the hot air balloon was, in my opinion. But it's okay. We can fix this. So just like I did before, we're going to first do 180 minus 62. It's going to give me 118 degrees here. And then this angle here is going to be 180 minus 118 minus 49, and that gives me 13 degrees in that corner there. So here's my slightly different right or oblique triangle. So we got 650 is the distance between. This is going to be 118. This will still be X and Y. I'll do it that way. This will be 13. And then this is 49 degrees here. Okay. So now I have everything I need to set up my law of sines. Again, I'm looking for side lengths. I'm going to set this up as 650 over the sine of 13. And that will equal to X over the sine of 49. And I'm also going to do this a second time and do, yeah, I got space over here. 650 over the sine of 13 is equal to y over the sine of 118. Okay. So again, if I multiply through, I'm going to rewrite this. It'll be 650 multiplied by the sine of 49 divided by the sine of 13 is equal to x. 650 times the sine of 118 over the sine of 13, and that's going to equal to y. Okay, so for this case, I'm going to assume I'll just do round to the nearest, we'll go round to the nearest 10th. So I can put that in my calculator and calculate both of these out for x and y. So 650 times the sine of 49 divided by the sine of 13. This is going to give me 2,180.8 feet for x here. So that is the distance to the first building. And then I do the same thing with my other equation. And that's going to give me 2,551.3 for my distance to the second building. Okay. So that is our law of sines in those cases there. The other thing I want to talk about in this video is going to be law of cosines. So law of cosines is very specifically when you don't have an angle side pair. Okay, so we did law of sines as long as we know one side and the angle across from it. If we don't have that, we're going to probably use law of cosines. So in this case, here's my setup in three different possibilities. Still the same definition for A, B, and C with capital letters and lowercase letters. But in this case, I like to look at this pattern. So it's always going to be whatever, if you're looking for a side length for like that, it'd be A squared, then it's going to be cosine of A. They always match up. B squared, cosine B, C squared, cosine C. Whatever you start with, like for A squared, then it's the other letters. So we have our B squared plus C squared minus 2BC. This pattern repeats. Since I'm using B squared here, then it's A squared plus C squared minus 2AC. Now, the trickiest thing about these is going to be how you multiply through and keep track of everything. So when I do these, I like to do it step by step until I get to one final thing that I can plug in at once. So let's take a look at one of those examples right here. So again, we want to solve for a triangle ABC, round side lengths to the nearest tenth and angle measures to the nearest degree. So first thing is, and the way I have it set up, here's I'm looking for A. So I know that I can set it up as A squared is equal to B squared plus C squared minus 2BC times the cosine of A. So I've got all of those pieces. I got B, C, and A there. Okay, so this will be B, and then this will be C. So A squared is equal to B squared plus C squared minus 2 times B times C times the cosine of 39.4. So it's a matter of order of operations. I'm going to go ahead and square these and multiply these as kind of their own steps here. So that A squared is equal to 144 plus 196 minus, that'll be 2 times 12 times 14 minus 336 times the cosine of 39.4. Okay. So now, again, the key part about this one is these are basically three separate numbers. I am going to multiply negative 336 times the cosine of 39.4. Okay, so negative 336 times the cosine, 39.4. So A squared is equal to 144 plus 186 minus 259.638. From there, we can go ahead and put all these numbers together through addition subtraction. So I'll do that. And I get 80.36615, we'll say. So again, everything here, you don't have to do all these steps on your own step by step, but I like to see all the math as I go through just to make sure it's clear. Now I could square root both those sides there. My A value comes out to 8 point, and we want to round to the nearest tenth. So it's 8.96, so it's actually going to be 9.0. Okay, so it actually came out as 8.96. Okay, so that's my A value. Now, again, with solving, we need to find all of our missing angles. One thing that makes this a little bit easier, I don't have to do law of cosines again. Instead, now that I have A and 39.4, we can do law of sines. We have an angle side pair. So that's my strategy that I'm going to do for this. So I'm going to start with I'm going to start with angle C here. So that means it's going to be the sine of C divided by lowercase c, which is 14, is equal to the sine of 39.4 divided by 9.0. Now, for my purposes here, I'm actually not going to use 9.0. I'm going to use from my calculator this decimal number. Okay, it's better to use the decimal number that you did not round off as part of your calculations. So in this case, I'm going to have the sine of C, if I multiply both sides by 14 here, oops, that'll be 14 times the sine of 39.4 divided by 9.0. So that means C is equal to the inverse sine of all of this. So just like when I did my law of sines, I like to have it set up here. This is what I write this all down, and then this is what goes in my calculator. Again, this is going to come from this number here. Okay, I don't want to round off that number because I want to be as accurate as possible. So I'm going to do inverse sine, and that's going to be 14 times the sine, 39.4, divided by that 8.96 number. And I get for the angle C here, it'll be 82.4, but I'm going to round it off to the nearest degree. So it's just going to be 82 degrees there. So that is the measure of angle C. Now that I have that, just find the angle B from 180. So 180 degrees minus 39.4 minus 82. So do that real quick. And I get, well, technically I get 58.6 thanks to that 39.4, but I'll round that off. So the measure of angle B is going to be 59 degrees there. Okay, so technically I'm rounding, if I'm going the directions, I'm saying rounding to the nearest degree, that'll be 59 degrees, even though it should have the decimal thanks to the 39.4. All right, law of cosines can be a lot of work, especially when we're finding those missing pieces, but it's just get used to those step by step there. One more way we're going to use our law of cosines, and that's going to be finding an angle given a scenario where we don't know any side lengths. So a triangular area of a lawn has a sprinkler located at each vertex. So we're going to just make our little triangle here. Okay, those are 3 little sprinklers. If the sides of the lawn are 19 feet, 24.3 feet, and 21.8 feet, what angle of sweep should each sprinkler be set to cover? Okay. Sorry, just getting thrown off a little bit by that one. Okay, so I'm going to go ahead and label this 24.3. This will be 19 here, and this will be 21.8. Okay, so the idea is that we want to find all 3 angles here because that will tell us what each angle of sweep is supposed to be for each sprinkler. So in this scenario, I have no angles that are known. So I'm going to say this is going to be angle A, B is going to be right here, and C is going to be right here because they're across from A, B, and C. So I'll just pick one to start with. So if I start with A, for example, so it's actually probably, let's see here. You know what? Give me 1 second here, sorry. So I'm actually going to start with B here instead, because I'm going to set that up so that we always want to start with the longest side. And I think that makes it easier because potentially there are things that can come up with multiple possibilities for triangles if we start with like the 19 here. But I'm going to start with that one. So B squared is equal to A squared plus C squared minus 2 times A times C times the cosine of B here. So the one thing I don't know is B. So I'm actually going to work this formula to get a brand new one for cosine B. I'm going to solve for this. So to do that, I'm actually going to start by subtracting these over. So that's B squared minus A squared minus C squared is equal to negative 2 times A times C times the cosine of B. Divide both sides by negative 2AC here. It's up to you if you want to rearrange this because we're dividing by a negative like this. We can actually swap all the signs for B squared, A squared, and C squared. So what I mean by that is that's going to look like this. A squared plus C squared minus B squared over 2 times A times C is equal to the cosine of B. Okay, so now this is technically a different formula that I could use if I want to find the angle of B. And more specifically, it's going to be the inverse cosine of all of this now. So that's why I can use the evaluate here. So in this case, I'm going to do 19 squared plus C squared, which is 21.8 squared, minus B squared, which is 24.3 squared, over 2 times A, which is 19, times C, 21.8. Okay. And the inverse of cosine of that is going to tell me my measure of my angle B. So I'll do inverse cosine. That will be, let's see here, 19 squared plus 21.8 squared minus 24.3 squared divided by 2 times 19 times 21.8. So that means I get 72 point, we'll just go one decimal place, 72.7 degrees for the measure of angle B. Now for everything else, we have one angle pair like this. I could do law of sines. So if I want to do, for example, the sine of, we'll do sine of A over 19 is equal to the, let's see here, sine of 72.7 over B, which is 24.3. Okay. So if I kind of rearrange this and everything like that, it's going to be inverse sine of 19 times the sine of 72.7 over 24.3. So the measure, plug that in real quick, will be 19 times the sine that divided by 24.3, and I get 48.3 degrees there. And then for my final angle, I'll just do the 180. So the measure of angle C is equal to 180 minus 72.7 minus 48.3. So 180 minus both of those. And I get 58 technically 0.0 degrees there. Okay. And that is it for our law of cosines with our missing angles altogether. All right. Take care, everybody. I'll see you next time.